Welcome to our short and sweet series. So we're going to try to present some calculus topics in a condensed nutshell. Not really meant to be an all-encompassing or comprehensive introduction to the topic, but maybe you're just reviewing for an exam and you've landed in this spot, and we're glad to have you here. So we're looking at integration by parts, a really cool topic. It's kind of a badge of honor, a significant milestone as you get going. And here's our formula that we need to know. We need to know that the integral of some function u times function dv is equal to uv minus the integral of v du. And a lot of times, and of course the foundation is that both u and v are some functions of x and they have continuous derivatives. And I usually like to start with my u. Okay, I'm going to let u equal a log function if I have it. If not, I'm going to look for inverse trig functions like arcsine, arctangent, or I'll look for an algebraic function like x squared, or a trig function or an exponential function. Then what you want to keep in mind is dv has got to be everything else that's left over. Okay, everything has to be accounted for in either the u or the dv statement. So integration by parts, first of all, how do I even know when to use it? I think that's half the battle. Can I just get away with a traditional u substitution, or do I actually have to use this big bear integration by parts? The key is you want to look for the product. Okay, you want to look for the product between an algebraic and a transcendental function. Now, when we say algebraic, just basically think of your typical polynomial like an x or a 3x or an x squared. And then a transcendental is essentially anything that's not algebraic. It's this all-encompassing group of it's a lump sum of all your exponential functions, your log functions, your trig functions, everything else. Okay. So we're going to take a peek at a couple of examples here, and in just a really classic warm-up question here. We've got this algebraic expression 2x, and then it's multiplying e to the x. So we've identified the product, and it's certainly a product between an algebraic and a transcendental function. And going through my L.I.A.T.E list, I let u equal this 2x. Now, what you want to do from there is you calculate his derivative. So we could say du is equal to 2 dx. By virtue of what you picked for u, the leftover portion was not just e to the x, but also the dx. So everything in here got accounted for either in the u or the dv. Now, what you want to do there is integrate the dv, and you'll get v equals e to the x. Don't worry about the plus c on that term. We'll take that into account in the last step. So we know that we need uv minus the integral of v du. So in this case, it's going to be 2x times e to the x minus the integral of e to the x times 2 dx. Now, a lot of times I like to grab that 2, and I'm just going to slide it out here and then just do a real simple integral. So we're going to get 2x e to the x minus 2 e to the x plus c. This is my final answer. That's my antiderivative, and a really nice check. And same could be said for all of your integrals, is just derive this expression. And when you finish deriving, you'll get this bear. All right. Another really common example that I've seen more and more of is this integral of x times f prime of x. And what makes this one more challenging is this f prime is a mystery. We don't know explicitly who that is. We don't know if it's a natural log or an e, or what exactly it is. But so you might have to do some trial and error, and that's not unheard of, where you kind of say, okay, what if I let u equal maybe x, maybe f prime of x? The problem is, and this is what I've always said, if I let u equal f prime, then the du would be f double prime, and it generally feels like you're kind of trending in the wrong direction. So what I wanted to do is I wanted to let dv be f prime, so that when I integrated, I got back to f, and now I feel like I'm kind of going closer to home, so to speak. So let's take a look at what this integral is going to look like if we do u times v minus the integral of v du. Now you'll notice what else this integral, or this example, has is it's got bounds. So we got a bound from a to b here. So what I'm going to do is I'm going to denote that right here. I'm going to say from a to b, and I'm also going to denote it right here. So if I go ahead and plug in that first set of bounds, I'll get b times f of b minus a times f of a So that takes care of this bear right there. Now, as far as this integral goes, either you're going to have some kind of information. A lot of times they're going to give you a graph of lowercase f. So then that integral right here just measures the area bounded between f and the x-axis, and you can import that area. Or there'll be some type of other given that's going to help you solve that. Or worst case scenario, we'll say that the antiderivative of lowercase f is a capital F, and you can go ahead and plug in your bounds accordingly there. So that's all we'll say for now in this general example. So I hope that helps. Good luck the next time you see integration by parts.